So in this video we are going to be looking at mostly buffers, how they are created, and ultimately how they are affected by acids and bases when they are added, and then also a weak base problem as well. So in number one it says calculate the pH of a buffer that is 0.105 molar sodium hydrogen carbonate and 0.125 molar sodium carbonate. So with part A, what you should be looking at immediately is what acid-base system do you have present. So I'm seeing HCO3 and CO3 as well. So when you take your appendix D out, you're looking for something that is similar to that. And if you go down, you'll see carbonic acid, which is HCO. It also has two Ka values that we have to decide which set we will use. So carbonic acid, H2CO3, will dissociate into HCO3 minus plus H plus, and HCO3 minus dissociating into carbonate and H plus. And this represents Ka1 and this represents Ka2. So now what we do is we try and identify what is present. So we have a carbonate and HCO3 present. We completely ignore the sodium or whatever counterion it is. Counterions are easy to identify because generally they're group 1 or group 2, mostly group 1 elements. So you're looking for sodium or potassium. So we're looking for the equation that has both HCO3 and CO3, and that would be the second one. So we're going to use Ka2, which is 5.6 times 10 to the negative 11. And that doesn't really matter what Ka1 is because we're not really going to use it. We already have concentration, so we can jump in and use pH equals pKa plus the log of the concentration of the base over the concentration of the acid. And that's equal to the negative log of 5.6 times 10 to the negative 11, the Ka, plus the log of the base, 0.125, over the acid, 0.105. So when you do this problem, the way to identify what the base is and what the acid is very simple. The one with the fewer hydrogens is likely going to be the base. So we have a buffer present. So 5.6 exponent 11 negative. Take the log and hit the negative of it. Is 10.25 plus 0.125 0.076. Add that to my original number, and that end equals 10.33. So that would be the pH of that particular mixture. For the second part, we have a similar approach to what we're doing, but we are basically just going to be using different or unequal concentrations. So for the next problem, what we'll have to do, we'll have to take into consideration that we are combining two different volumes, whereas above we kind of assumed that we were mixing equal volumes. So what we will have to do is determine the new concentration, because when you mix two solutions, you're diluting them because the volume is increasing, but the number of moles is staying the same. So what we can write is pH equals pKa, which is 10.25. That doesn't change. Plus the log. We're going to write a big bracket here and try and solve what we're doing. So we have our base. We have 0.075 liters times 0.15 moles per liter of the sodium carbonate. Divide it by 0.140 liters, which is the total volume of the mixture. And on the bottom, we'll do 0.065 liters times 0.20 moles per liter. And we'll divide that all over 140 milliliters. So we have a relatively big equation here. But when we resolve it all out, we get a pH of 10.19. So we multiply the top first, divide by 0.14, multiply the top, divide by 0.14, take the quotient of that, take the log of it, and we should add up and get a difference of 0.06 negative. That's how we get the pH of the first one. So the next question is very, very similar. It basically is asking us to do the same thing as we just did, but with the masses of compounds. So we're going to write this, or I'm going to write this as the dissociation of ammonium into ammonia plus H plus. And all of these compounds are aqueous. Now, I can't find the Ka value for ammonium, so I have to use the Kb value for ammonia. Then using Kw, I will convert it. So I can find the Kb value in Appendix D. So to get the Ka value for the acid ammonium, I'm going to say Ka is equal to Kw over Kb is equal to 1.0 times 10 to the negative 14 over 1.8 times 10 to the negative 5. And for this particular problem, I get 5.6 times 10 to the negative 10. So that would be the Ka for this particular process. Now we get the concentrations of these compounds. So first up is ammonia. The concentration of ammonia is equal to 7.0 grams of NH3 in 2.50 liters times 1 mole of NH3 over 17 grams. So that will turn me into moles per liter. And that equals 0.1647 moles per liter NH3. I do the same thing with ammonium chloride. 20 grams NH4Cl over 2.50 liters times 1 mole NH4Cl over 53.50 grams of NH4Cl, 0.1495 moles per liter NH4Cl. So there's several different ways that we can deal with this. We can use an icebox method to get our final answer, or we can just use Ka. So without using the Henderson-Hasselbalch equation, which will work here, we can actually solve it. Ka is equal to the concentration of NH3 times the concentration of H plus all over the concentration of NH4. So we have this reaction, we have Ka, we solve for it up here. We have the concentration of ammonia and ammonium. and we can just rearrange and solve for H. So the concentration of H plus is equal to Ka times NH4 plus over NH3 equals 5.6 times 10 to the negative 10. NH4 is 0.1495 over 0.1647, which is the ammonia. Now, we would have plus x and minus x in this if we're doing the icebox method, but we're assuming that the loss of x, or the change in concentration due to x, is insignificant. So the concentration of H plus is equal to 5.047 times 10 to the negative 10. And then take the negative log of that number. The pH equals 9.30. So now we're just going to look at least extend what we've done in class to look at what happens when we add an acid or a base. So if you were adding a few drops of nitric acid, you're adding H plus and nitrate. Nitric acid will react with the base, which is the ammonia. The proton will attack those electrons, and we get NH4 plus NO3 negative. And we're going to include nitrate, which is a spectator, because the question asks for the complete equation. For part C, we're adding a base of potassium hydroxide, so K plus OH negative. So you have to be aware that these are strong electrolytes. So nitric acid is one of the 7 strong acids, so I know it'll automatically break into H plus and NO3 minus 1. And potassium hydroxide is a strong base, so it will completely break up into its ions. And I will react this with the acid. The hydrogen from the ammonium will attack the hydroxide, to form water, and give me NH3 plus K plus. And that's the complete ionic equations. If we were asked to write net ionic equations, we would be removing the nitrate or the potassium. So for question 4, you are being asked to create a buffer. And the reason that this question is a really great question is because you're being given pairs of 0.10 molar solutions, and you are first being asked to determine the right pair, and then you are being asked to determine the right quantities of these solutions to make a 1 liter final solution. So there's two little constraints there. So the first thing we have is we have formic acid and sodium formate. We have propanoic acid and sodium propanate. And we have phosphoric acid and sodium hydrogen phosphate, sodium dihydrogen phosphate specifically. So you have these 3 compounds, and you have them present in the concentration of 0.1. So what you need to do is you need to take your appendix D and find these compounds. And you need to find the pKa value that is closest to each one. So what you would do is you go down and find formic acid, and it has a concentration, or a Ka, of 1.8 times 10 to the negative 4. I would take the log and realize that its Ka is 3.74. So that's outside 1 unit from the desired pH. So that's not going to be ideal. The next one I'm going to look at is the phosphoric acid. I'm going to look at the first proton, And the first Ka for phosphoric acid is 7.5 exponent 3 negative. And I'm going to take the log of that and negative, and that's 2.12, and that's way too outside the range. It's over 2 units away. So the third one's probably going to be our best one. It's propanoic acid, and it's 1.3 exponent 5 negative. I'm going to take the log of the negative, and it's 4.88, so it's 8 hundredths, 8.6 hundredths away from what I want. So that probably is going to be the one that I'll use. Remember that pH range should be within, for the best effect, you should have your pKa of the acid-base pair that you're using to be within 1 unit of your desired pH. So when you look up the pKa of each of these, we got 3.74, 4.89, and 2.12, those three. This would clearly be your choice. So when you look at this, you know that this is going to be your acid, and this is going to be your base. So we've picked our pair, and now we have to actually go to work. So the first thing that we're going to do is we're going to pull out our Henderson-Hasselbalch equation. I know what my desired pH is, I know what the pKa is, so I'm going to substitute values in to get my log B over A. So I want 4.80. My pKa is 4.89. So negative 0.0861 is equal to the log of B over A. 10 to the x, 0.8202 equals the ratio of base to acid. So I know right off the bat that I'm going to need more acid than base to make this work, which makes sense because you want our pH to be lower than our pKa. And we now have a little bit of an issue because we only want a liter of the buffer. So we're going to make, we have to make one of them to be an unknown. So I'm going to say that let's let y equal the volume of the base, and therefore 1 minus y is the volume of the acid. So I know 0.8202 is equal to the concentration of the base. So 0.10 molar, and that's just our stock solution, times the volume of the base, divided by the total volume, which is 1 liter. And then I'm just writing in the 1 liter because in a question that would be similar to this, it might be a different volume. And then 0.10 molar times 1 minus y divided by 1 liter. Now we're just doing math. We can kind of ignore those 1 liters at this point. So we just solve for y, and we get y equals 0.4506, which is in liters. Therefore, the volume of the base would be 1 minus that. So the volume of the propanoic acid, C2H5COOH, is equal to 549 milliliters. The volume of the sodium is equal to 451 milliliters. And we make sure that when we add those up, we get 1 liter, which is, based on how we solved it, would be impossible if we didn't. So finally, what we're going to look at is just determining the pH of a weak base. So remember that your weak bases, according to Lewis, are electron donors, and nitrogens are great because they have a lone pair on the nitrogen, so they're perfect electron donors, making them bases. So we have anions that are bases, but anything that has a lone pair generally can act like a base. We see things like BF3, which are lacking their octet around the center atom, and they can actually behave like acids or Lewis acids. So when we put a base in water, we have NH3 plus H2O is in equilibrium with NH4 plus OH negative. So a base is anything that increases the concentration of OH. A base is a hydrogen acceptor, and a base, according to Lewis, is an electron donor. So ammonia meets all three of these particular definitions of an acid or base, and those three definitions are something that we need to know. So we'll turn this into an ice box. Water is a liquid. I didn't write that in. We'll assume the other ones are aqueous. And we just are going to go to work. So 0.01, assume we start with 0. The change is minus x, x, x. 0.01 minus x. Those are plus x's. It gives me x. So Kb is equal to the concentration of OH minus times the concentration of NH4 plus over the concentration of NH3. So 1.8 times 10 to the negative 5 is the Kb value for ammonia in Appendix D, is equal to x squared over 0.01 minus x. We'll just continue treating this as if we cannot ignore x. So from here we go into the quadratic form, just to simplify this process, because I know that you can do it at this point. We can solve for x, and we get 4.15 times 10 to the negative 4. That's moles per liter. I probably don't need the parentheses here. This is equal to the concentration of OH negative. So the negative log of this gives me a POH equal to 3.38. pH is equal to 14 minus POH is equal to 10.6. So the concentration of H plus is obviously always controlled by the concentration of OH. The method for solving a weak base is exactly the same as every equilibrium problem that we've done. If we go and we check to see if we could have ignored X, we see that we're at 555. It is just at that point where you got to make a judgment call. If you didn't ignore X, you're 10.6, which is the same.